Okay, this you probably haven't seen before, Markov's inequality and Chebyshev's inequality. These are lovely math facts that hold for lists of numbers. Markov's inequality holds for lists of numbers if every element of the list is greater than or equal to 0. Chebyshev's inequality holds for any list whatsoever. We are going to come across analogs of these inequalities later on for probability distributions when we get to probability and random variables. Well, let me just talk about what they are. We mentioned when talking about the mean that a light person on a seesaw can balance a heavy person if the light person sits far away from the fulcrum, right? If you sit really far out and the other person is close in, the heavy person is close in, then a light person can balance a heavy one. Well, if we know that the person on one end can't be any further away from the fulcrum than a certain amount, we know that they've got their back to a wall, basically. That tells us something about how far away a light person could be sitting, or that if a person that were sitting very, very far away weighed very much, this couldn't balance. This person would be up. Okay? So if this person has their back to a wall, then we can learn something about how big a person could be sitting how far away and have this still balance. All right, so that's what Markov's inequality is telling us. Let's make it quantitative. It's basically this. If you have a list of numbers and none of the numbers is negative, and the mean of the list is m, then the fraction of numbers in the list that are greater than or equal to x can't be any bigger than the mean of the list divided by x. And this is true for all numbers, all numbers x. It's not very useful unless x is bigger than 1, because otherwise you're saying that the fraction is, the fraction is less than something that's bigger than 100%, right? It's sort of not helpful. Okay. Sorry, it's not useful unless x is bigger than the mean. Otherwise, you're saying that it's less than or equal to something that's not helpful. Okay, so this is really turning into math that intuition about if the back's against the wall, then you couldn't have a very big person very, very, very far out because this person, it wouldn't balance anymore at the fulcrum. If you're interested in how to derive it, it's in here. All right. When is this useful? Well, if we know that from first principles that some list can't have any negative numbers, and we'd like to get some idea of how many extreme values, how many large values there could be, we can use Markov's inequality to limit that. Okay, we won't know what the exact answer is, but we can get a bound on it. So let's suppose that there's 200 students in a class. On average, they have $15 in their pocket. How many could have $75 or more? Okay, so I'm assuming that nobody is carrying around debt in their pocket, right? That the amount of money in your pocket is at least 0. Yes? So we have a list of 200 numbers each number is at least 0. We know that the average of the numbers is 15. How many of the numbers could be bigger than 75? Okay. Well, Markov's inequality says the fraction that have 75 or more in their pockets, that's the fraction that's greater than or equal to x, is less than or equal to the mean of the list divided by x, okay, which in this case is 0.2, 20%. 5 times 15 is 75.